Welcome! In this differential equations tutorial, we are going to solve some initial value problems numerically, but on paper I'm going to do some analytically also. So if you're interested in that, then stick around. All right, so let's begin with question 1, where we're going to do this analytically before we start solving these initial value problems numerically. So it's useful to be able to do it in two ways in the beginning, because then you can see what's going on, comparing the analytic solution to the numeric solution, which will be a collection of points. All right, so let's begin with question 1 here on my list, and I think I should probably zoom in on this. Okay, so we've got an initial value problem. Y dash is y squared plus 1, where y of 0 is 0. And so what we want to do is write this y dash as dy on dx. Because this equation is separable, it will clarify how to separate this. So we take our dx to the right hand side, divide by y squared plus 1, and so we can write dy on y squared plus 1 is the integral of 1 dx. So we want to integrate the left hand side because that's the more difficult of the two integrals. The right hand side is really easy. We just have x plus c. Okay, but on the left hand side, we're going to need to make a trigonometric substitution. So we say let y equal tan of theta. Okay, so we want to do this in terms of theta. And why I've chosen tan of theta, because via experience, I know that this is going to work out, but there's a little hint there in the denominator, because tan squared plus 1 can be viewed as sine squared over cos squared plus, and then you multiply throughout by cos squared, and you end up with cos squared over sine squared plus cos squared. But sine squared plus cos squared is 1, so we just end up with the integral of cos squared. Let's write down the details here. Okay, so we have y equals sine theta over cos theta, and so remember we want to differentiate y with respect to theta. So dy on d theta is using the quotient rule. We have 1 on cos squared theta, v, which is this one. This one is u, v, cos of theta, times the derivative with respect to theta of u, sine theta, minus, and then we swap these around. So minus sine theta times the derivative with respect to theta of cos theta in that big bracket. Okay, so let's differentiate those two. The derivative of sine is cos, so we have cos squared theta there. The derivative of cos is minus sine, so then we end up with plus sine squared theta there. And so since cos squared theta plus sine squared theta is 1, we just have 1 over cos squared theta. That's called sec squared theta. Okay, and so this tells us then how to replace dy and write dy in terms of d theta. So this says we can replace dy with sec squared theta, d theta, up in here. So let's go ahead and do that. And then on the denominator, we have tan squared theta plus 1. Okay, and so we need to do some simplifying here, because remember tan is sine over cos, so sine squared over cos squared, but then we multiply top and bottom by cos squared, and so we have cos squared theta. Remember sec squared is 1 on cos squared, so let's write that 1 on cos squared theta. And then on the denominator we have, since we have multiplied through by cos squared on the top and the bottom here, we have sine squared theta plus cos squared theta times 1, which is cos squared theta. Okay, now since sine squared theta plus cos squared theta is 1, and these cancel, we just have the integral of 1 with respect to theta. And so we can write that as theta plus a constant, but we already have a constant on our left-hand side up here. Okay, so we're nearly done. So now we've worked out that theta is x plus c. I mean, we don't really need this c here because we have 1 on the right hand side. We only need one of the c's. All right, but what was theta? It's the inverse tangent of y. Okay, so arctan, let's write for that. Tan of y is x plus c. Okay, so let's take tan of both sides, and so then we get y as a function of x is tan of x plus c. Okay, now y of 0 is 0, so when x is 0, y is 0. So what we have then is tan of c is 0. And so we can have c equals 0 because tan of 0 is sine of 0 over cos of 0, which is 0 over 1, which is 0. So we get c equals 0. Okay, hence y of x is tan of x. All right, so now that we've done that, let's go to Mathematica where we can start running some numerical methods. All right, so I need to look at that problem set again. What are we doing? We're solving. So question 2 says solve the IVP. Y dash equals y squared plus 1. Y of 0 is 0 with step size 0.1 over the interval from 0 to 1, but do this with Euler's method. So recall what Euler's method is again. If I scroll up here, we have xn plus 1 is xn plus h, and so this is xn plus 0.1. Yn plus 1 is yn plus h, f xn yn. All right, now f is just the right-hand side, and so this is yn plus 1 is yn plus 0.1 times yn squared plus 1. Okay, and so this is the sequence that we want to run, this together with this. So let's go to that implementation in Mathematica. So what I'm doing here, I put the step size in, I define that function. Here it's defined in terms of a and b. So what does this look like in our case? Well, this would just be b squared plus 1. All right, now y of 0 is 0, so we need to change that y subscript 0 to 0. So we've got the initial point 0, 0. And now in steps of 0.1, we need to go to, it's 1 over h, and then minus 1. Okay, so let's just check what this is in this case. That's 9. Okay, and so now just to automate that, I need to change that 0.8 as well to 0.1 times m, let's say, where m is this number, which hopefully will be an integer. Okay, so let's call this m, and then this would be m, and then down here this should be m times h. Okay, so let's do that again. Good. Now let's overlay on that a plot of tan as x goes from 0 to 1. That into memory here, and then I will incorporate that into the show part of this. Okay, so there we go. I've got tan there, and you can see that with a step size of 0.1, the points eventually are drifting away from solution because errors are building itself. Okay, so that completes question 2. So in the next one, we're asked to use RK4 to solve the same equation. So I'm going to copy out certain things in here, like the first 4 lines of this. And then where it says B, we've got to change that to H times M. So I'll scroll down to RK4. Down here where it says 0.8, we'll change that to H times M. And then we also wanted to include the plot of tan so we can compare. What? It should be m. Okay, so there we go. Now our analytic solution, don't want that there. This is still here. Okay, so now making all of those modifications to the RK4 piece of code. All right, so that's these first lines, and then I've changed this down here to include tan. Okay, so let's run this. And there we go. This looks pretty close to me. So this completes question 3, which is to solve that same equation using RK4. Okay, so now we're going to do question 4, which is this initial value problem again using RK4, but this time we're not going to enter all of the points into memory. In other words, suppose you had a differential equation that required like 10 million points, and suppose your computer was pretty limited and you didn't want to overflow the memory. So how would you do it in that case rather than using table like what I have in my code? Okay, and so let's have a look. So we want to make modifications to this. So I'm going to copy this out and I'll show you how I think about this just from scratch. So in other words, we don't want tables, so we'll get rid of this and I'll sort of break this apart. All right, we still have all of these, but what we want to do rather than use table and tabulate all of the values, what we want to do instead is use a for loop or a while loop, etc. So I'm going to open up the Mathematica help file. And I'll just put in for All right, let's copy something out, browsing the structure here. Okay, so let's try this. Okay, so what this does is it just prints out 0, 1, 2, 3. Okay, and so we want, in our case, we want to do this over n. Let's change that to n. Same thing. All right, now what we want to do is update. So what we're doing here is saying x equals x plus h, and then let's print the new x. Up above, we'll say x equals 0, and h is 0.1. Okay, and so this will be updating the x values, but you see x is getting replaced with the previous x value. We're not storing in memory all the previous x values. Now, what we want to do is do the same thing with y. Okay, so replacing the yn with y, placing the xn with x, and we're going to print the pairs x and y. Okay, but I can see a little problem with this. We've got to do this, the two of these simultaneously, so that I don't put xn plus 1 here. So let's put in a pair instead. So x comma y is equal to the pair. Need to update what x is in here inside the pair. I think this looks fine. Let's run this. Okay, we need to include our functions in here. Up above that, we had our initial values. All right, so these look. What I want to do, though, is just double check. Oh, did I modify this? No, that's a copy, isn't it? Okay, all right, and then, so what I want to do is come up here and display sum of A, so we can compare that. Paste it here so we can see. No, these don't look the same, do they? Yeah, I'm missing K4, right? Somehow I'm missing K4 in that. Okay, so no subscripts this time. Okay, let's try that again. All right, so this seems good now. These match these, so we've sort of done that, but I need to take this higher than to 0.4. So what we do is change this n less than 10. Okay, so that does it there. And so these are not being put into memory, all of these previous terms. They're just getting printed out and updated. All right, so that completes that question.